Today we are going to address a very good question, that what happens when we exceed the allowable range. In this session we will talk about the range exceeding condition of integers, both signed and unsigned, and similar concept is adopted on other data types as well. So let's get started. Here in this example, I had provided an integer variable and that too an unsigned integer variable and assigned it a value 4294967295, which is the maximum allowable value of an unsigned integer. Let's see what happens when we try to execute this code. And this is what we are getting as a result, 4294967295. Now this is quite expected, right? Let's change the value a little bit. I'd exceeded this value to 1 and make it 4294967296 and see what will happen when we try to exceed the range. We are getting values equals to 0. Now this is quite weird, isn't it? To understand why this happened when we try to exceed the range, we come back to 0 again. We need to take one short example to help illustrate the fact. In this example, I'm taking a 3-bit data and have written all the possible combinations of a 3-bit representation. We can say 000, 001, 010, 011, 100, 101, 110 and 111. We are having the value from 0 to 7 for a 3-bit representation. The minimum value would be equals to 0 and the maximum value is equals to 7. And this is our range. Okay, let's see what happens when we try to represent the value 1 greater than 7. That is 8. We won't be able to represent this value 8 in a 3-bit representation. As you can see, 4th bit place value is equals to 2 raised to the power 3. Therefore, if we want to represent value 8, we need to set this bit and rest of the bits we need to reset. If we force ourselves to represent the value 8 in a 3-bit representation, then we won't be able to do that and we left with these 3 bits only. As this 4th bit won't be able to represent in our 3-bit representation, therefore we can say that in a 3-bit we are getting this value as equals to 0. As in 3-bit representation, this 1 bit is hidden and with the rest of the bits this is equals to 0. If we want to represent the value 1 higher than that, that is 9, we won't be able to represent that as well because this 4th bit is not available to us and we are just available with these 3 bits. Therefore, whatever is there inside these 3 bits, we would be able to represent that only, and that is equals to 1 in this case. If we try to represent the value 10, then similarly we won't be able to represent that because of this bit is not available to us. This is actually equal to 2 in decimal. For 11, this is equals to 3. As you can see in this example of 3-bit representation, our range is from 0 to 7. And if we try to exceed the range, we come back again to 0, and then 1, then 2, and then 3, and so on. That means we are actually performing some kind of cycle or something, starting from 0 itself to up to 7, and then 0, then 1, then 2, then 3, then 4, then 5, 6, 7, and again 0, 1, 2, 3, and so on. This is nothing but acting like a mod function. And in this example of 3-bit representation, this is mod 8 function or mod 2 raised to the power 3 function. This is because if we try to represent the value 8, why we are getting value is equals to 0? Because we apply 8 mod 8, which is equals to 0. Mod gives us the remainder, and this is the difference between a division and a mod function. Division provides us the quotient as a result, and mod gives us the result as a remainder. Therefore, when we divide 8 by 8, we get result is equals to 0. Similarly, if we try to divide 9 by 8, we get result is equals to 1 because remainder is equals to 1. And if we divide 10 by 8, we get remainder is equals to 2 and so on. Similarly, for a 32-bit representation, if you try to exceed the range, then you have to consider one extra bit, that is 33rd bit. But as we are available with only 32 bits, therefore there is no way we would be able to represent higher value than the maximum value, and we come back again to 0. We can say that for 32-bit unsigned data, our mod function would be mod 2 raised to the power 32. For n-bit unsigned data, this would be mod 2 raised to the power n in general. Now let's talk about the signed range. Signed range is little different, but the idea is same. Let's again take an example of a 3-bit data. For a 3-bit data, signed range would be -4, 2, plus 3, according to 2's complement representation. Now it's quite easy to represent the number in 2's complement and see what happens. when we try to exceed the range, but it would be much better if we visualize it in a different way. Let's take an analogy of a clock. Like a clock is mod 12 function because when it's 13 o'clock, it means 1 o'clock. Isn't that so? Because we are available with numbers from 1 to 12. Therefore, if we want to represent 13, we are actually coming back to 1 again. Because 13 mod 12 is equals to 1. This clock analogy helps us in understanding these range exceeding conditions. Let's visualize this. As we know, for 32-bit unsigned integer, range would be from 0 to 4294967295. And if we try to exceed this maximum value, that is 4294967295 to 4294967296, we come back again to 0. Isn't that so? Therefore, in a similar case, the range of an signed integer is from minus 214748364 to plus 214748367. When we try to exceed the maximum value, that is 214748367 to plus 214748368, we actually get this value, that is minus 214748368. As this is the similar case that we had done in the case of unsigned, when we exceed this, we come back to 0. In the similar fashion, when we exceed this, we come back to this minimum value, minus 214748368. And if we try to represent number minus 214748369, which is one lesser than minus 214748368, we would come back to the maximum value, which is plus 214748367. Let's try to verify it by executing in code block. Here I have provided a signed integer variable. By default, integer variable is signed. And I provided the maximum value for a signed integer variable, that is 214748368, which is one greater than the maximum value. Let's see what happens when we try to execute this code. Isn't that our expected result? That is minus 214748368, which is the minimum value possible for a signed integer variable. Let's change the code a little bit. Change this to negative value and make it 9. And this is what we are getting as a result. 214748367, which is the maximum value in our signed integer. Okay friends, this is it for now. See you in the next lecture. Bye-bye.